गुड इवनिंग एंड अ वेरी वार्म वेलकम टू द ब्लैक होल। एक शेर से अगर मैं आगाज़ करूँ आज, जो ज़िंदगी थी मेरी जान तेरे साथ गई, बस अब तो उम्र के नक्शे में वक्त भरना है। ये तो थे अमजद इस्लाम अमजद। आज हमारे साथ हैं डॉक्टर सरमद अब्बासी, और वो भी नक्शों ही की बात करेंगे, लेकिन उनमें वक्त की बजाय रंग भरने का तस्करा होगा। आप जानते हैं डॉक्टर सरमद अब्बासी हर माह के पहले जुमे को हमारे साथ जो हैं मौजूद होते हैं। ख़ास तौर पे लाहौर से सफ़र करके आते हैं। गर्मी, सर्दी, आंधी, तूफ़ान किसी को ख़ातर में नहीं लाते, और वी आर वेरी ग्रेटफुल टू हिम फॉर दिस डेडिकेशन। डॉक्टर सरमद अब्बासी गुज़िश्ता 20-25 साल से दरस व तदरीस से वाबस्ता हैं। कई यूनिवर्सिटियों के साथ आप अपनी सर्विसेज दे चुके हैं। कीनली इंटरेस्टेड इन साइंस, द फिलोसफी ऑफ साइंस एंड रिसर्च एंड टीचिंग। मैथ कैट नामी यूट्यूब चैनल रन करते हैं टू प्रमोट मैथमेटिक्स एंड थ्योरेटिकल कंप्यूटर साइंस। करंटली यू आर एफिलिएटेड विथ एजुकेटिव एंड एड टेक कंपनी। और अगर आपको रियाजी खुश्क या बोर मजमून लगता है तो आई वुड सजेस्ट कि आप डॉक्टर सरमद अब्बासी के लेक्चर ज़रूर अटेंड करें, क्योंकि आपकी राय मेरा ख्याल है कि फिर तब्दील हो जाएगी। सो दोस्तों, प्लीज़ वेलकम डॉक्टर सरमद अब्बासी फॉर टुडेज टॉपिक, मैथमेटिक्स ऑफ मैप्स, कलरिंग मैप्स इज सम सीरियस फन। थैंक यू सर।
Okay, thank you so much, Naya. That's so great. It's so nice of you. Okay, so today I'm going to talk about how to color maps, all right? And I think a lot of people I see here are quite knowledgeable. So probably for you, this lecture would be something like that you already know. But then if you read the abstract, then I have said that in this lecture, I'll also talk about another notion called choosability, okay? The choice number of a graph, and that might be new for you. So, if you know all this stuff, just wait till that part. Okay, so in the 19th century, if you wanted to make maps, coloring maps was very expensive, right? Printing colored maps was very expensive. In fact, that was the case, about 50, 60 years ago. In Pakistani newspapers didn't have colored photographs and things like that. So, mathematicians wondered what is the smallest number of colors that you need to be able to color a map, all right? So, of course, you can just use one color, right? But the problem is that visually, it's very hard to separate two regions in a map, right? So it's desirable that if two regions share a border, then they should get different colors, right? So they asked the question, what is the smallest number of colors you need to color any possible map? And experience showed that 4 colors sufficed. Nobody could ever come up with a map which could not be colored with 4 colors. You needed a 5th one, right? So they formulated what is called the 4-color conjecture. And it took about 124 years to solve it. Okay, it kept mathematicians very, very busy. It was one of the most notorious, one of the most famous problems in mathematics. It was almost as famous as Fermat's last theorem, because the problem is so easy to state, and anyone, with the basic knowledge can understand what the question is, and yet nobody had any clue how to solve it. So that big triumph came in, I think, 1971 by 2 mathematicians in University of Illinois. I think there's a double P there, Apple and Harkin. Okay, and when they solved it, University of Illinois was so happy that the maths department got a special stamp made which said 4 colors suffice. Okay, and every envelope that came out of University of Illinois' maths department, they would stamp on it 4 colors suffice. So, and so today I can't prove the 4-color theorem. The proof is very difficult, right? So what we will do is we will prove what is called the 5-color theorem. All right, and that says, well, 5 colors suffice. So it's, very close to the 4-color theorem. Reducing that 1 is extremely difficult, okay? But the second theorem that I will prove is it has to do with something called the choice number, okay? And that I can explain in a different way. So nowadays, printing colored maps or looking on the screen is very easy, right? So it's money is no longer an issue. So what you can do is you can twist the problem and give it a very nice new modern way of thinking about it. Let's say now we allow as many colors as possible, lots of colors, right? But we let the people of the region choose colors for them. Okay? All right? So let's say you want to color the districts of Punjab, right? So you go to district Sahiwal and say, well, what kind of colors are acceptable to you? Right? And they say, well, we want green. Okay? And in that case, what will happen is if you have 2 bordering regions, if both of them choose the same color, then you can't satisfy them without 2 bordering regions having the same color. So what you do is you don't tell people to just choose one color. You ask them to choose more than one. Give them some alternatives. All right? And it turns out that if every region chooses 5 possible alternatives, okay, then you can color the map in such a way that everybody gets one of their choices and the bordering regions have different colors. Okay? And that to me that's a far deeper, bigger theorem, and it's best possible. Okay? If everybody chooses 4, then you might not be able to satisfy their requirements. Okay, so I have actually given a lecture on graph theory in which I have proved some of the things that I need here, but I'm going to reprove them because I want every sort of talk to be self-contained, right? So let's do that. So first of all, here's a map, right? And we want to color these regions. So in some way. Now, what graph theorists like to do is they don't like to color regions. They like to color what is called vertices. Okay? So they make what is called a dual graph. Right? So you put a vertex in every region, and then you connect the adjacent, the 2 vertices if their regions share a border. And you can go through this border. Okay? All right? Okay? All right? And now what you can do is you can actually say, I don't want to color the regions now. One more? Yeah. Oh, God. This.
Next bottom, southwest.
Yeah, this one. Yeah. One more. Top. This one. Yeah. Okay. Good. All right. And now what you can do is you can say, well, I can get rid of this white picture, and now I'm going to color the vertices, but 2 vertices that share that have an edge between them should get different colors. All right. So if I erase this, then I get then I can work with structures which are like this, rather than maps. So the detail which is not really essential to the problem, the boundary going in a strange way, is sort of abstracted out. So you have graphs like this, and this graph will also be planar. There will be no edge crossings, because you will connect this vertex to another vertex. You will go through the shared boundary, right? So you never have this crossing edges. So you have graphs like this, and these graphs have a property that they are drawn on the plane with no edges crossing. So this is a planar graph. This is called a planar graph. Okay, and for example, this graph is not planar because there's a edge crossing. So this is not a planar graph. Actually, this graph is inherently non-planar in the sense that you can't redraw it. It's not a bad drawing. The non-planarity is inherent in the graph. Okay, so these are planar graphs, and in a planar graph we have three objects that we can talk about. One is the vertices. So V is the vertices. Okay, and you can give them names. Okay, so here you can write down the vertex set. And then you have edges, which are actually pairs of vertices. Okay, so this is an edge, and it's actually the edge AB, and it's a set, it's unordered. Okay, so there is no direction to this edge. And this is an edge AE. But you also have these regions or faces. Okay, so for example, this is a face. Okay, this is a face. All right, so this one has actually 1, 2, 3, 4, 5, 6, 7, 8 faces. Okay, but mathematicians are weird. They say it has 9 faces. Right, the 9th face is called the outer face. Okay, all right, and yeah, one of the reasons is if you draw this on the sphere, okay, then there is no outer face. This, so usually, okay. And so we have our legendary hero, Euler. Okay. Euler, and he observed that if you take the vertices, subtract the edges and add the faces, you always get 2. Right? And this is sometimes, in many maths books, they say this is the second most beautiful equation in mathematics. All right? And the way he proved it was he just needed this eraser. Okay? He said that let's call this the Euler quantity. Okay, V minus E plus F. Okay, and let me go and erase one edge. So I get a new graph. In the new graph, okay, so let's call the Euler quantity of the new graph, the number of vertices remains the same. Okay, all right, the number of edges actually reduces by 1. Okay, but when I remove that edge, two faces were merged. So the faces also reduced by 1. Okay, so the Euler quantity remains unchanged. Thankfully, E and F have a different sign. So you keep doing that, and wow, the Euler quantity doesn't change, the Euler quantity doesn't change, the Euler quantity doesn't change. And then sometimes you run into problems like this. What do you do then? Okay, because now if you remove this edge, you don't create a new face. You don't merge two faces. So the argument gets stuck. In this case, what you do is this. Okay, you get rid of the vertex and you get rid of the edge. So once again, vertex and edges have different signs. Okay, so vertices go down by 1 and edges go down by 1, the faces remain the same. Okay, so the Euler quantity doesn't change. Okay, so that's cool, Let's keep doing this, just making sure we are not cheating. So the Euler quantity didn't change, it didn't change, it didn't change, it didn't change.
But that does not prove that the Euler quantity should equal 2, right? Because it can equal to anything. Anything and the argument will still apply.
Absolutely, except for I stop at when I have one vertex left, and then I count. So here, what is the number of vertices? What's the number of faces? 1,
edge is
0. So what is the Euler quantity for this graph? It's 2. So it must have been 2 to begin with. Okay? Yeah. So formally the argument is given by induction.
So constant of motion.
Yeah. 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 So it's a very nice argument, and it's really beautiful to explain it to, high school children or something like that. They really enjoy that. Okay. So that's one thing we will need. Okay. The second thing we need is what I call the first theorem of graph theory, and that's called the handshaking lemma. Okay, actually there are two, and I will state both of them. So let me draw another graph, and not a very complicated one, since I tend to just make things very complicated. So here's a graph, and there are vertices, and there is a concept of a degree of a vertex. Very simple concept. So degree of the vertex is the number of edges coming out of it, okay, or into it. It doesn't really matter because it's an undirected graph. So this has degree 2, 2, 1, 2, 3, 4, 5, 6. Yeah, 6, 1, 1, 2, 2. Okay? And the handshaking lemma says that the sum of degrees is equal to twice the number of edges. Okay? When I add up these, so 2 plus 2 plus 1 plus 6 plus 1 plus 2 plus 2, whatever that quantity is, it's twice the number of edges, which is actually 3, 4, 5, 6, 7, 8. So it should be 16. Okay? And you can check, because I'll just give you a proof. So the proof is this. Let me go to every vertex and put a red mark on every edge that's coming out of there. So I put 2 red marks here. I put 2 red marks here. I put 1, 2, 3, 4, 5, 6 here. 1 here, 1 here, 2 here, 2 here, 2 here, 2 here. So the total number of red marks that I put is the sum of the degrees. Every vertex had some degree, and I went around it and put a red mark. So total number of marks is sum of the degrees. Now let me zoom out. Let me look at this graph from far away, and I see that every edge is marked twice. Once from one endpoint and another times from another endpoint. So the number of red marks must be 2 times the number of edges. And therefore these two quantities are just counting the number of red marks in 2 different ways, and therefore they must be equal. And this is a very important theme in mathematics, in physics, in science, everywhere. If you can compute a same quantity in 2 different ways, then you can put an equal sign. And then you get an equation, and an equation has information in it. Okay, all right, but I'm going to prove another handshaking lemma that I will need. This is the classical one for graphs. This is the one that I think I will need. I'll see which one I need. I think I need this one. Yeah, and this may answer one question for you also. So this is a planar graph. So in a planar graph, I have faces. Okay? So the second handshaking lemma says that, oops, sum of the sides, sum of the number of sides in the faces, okay, this is equal to 2 times the number of edges. Okay? All right, so what does this mean? Let's first see this. So this face has 4 sides. So this is a 4, this has 3, this has 3, this has 3, and the outer one has 1, 2, 3, 4, 5, 6, 7. 7 sides. And it says if I add up all these numbers, I'll get twice the number of edges. Okay? So this is actually, I could say something like, oh, this is the same thing as doing it for the dual graph, using the handshaking lemma for the dual graph. But that, I don't need to do that. There's a very simple argument. Okay? Let me take the purple marker and put a dot on every, go around the face and put a dot on every edge. Okay, so 4 dots there, 3 dots there, 3 dots here, 3 dots here, and let's do the outer face also. So now you see why mathematicians insist on having the outer face, is to make things more elegant, right? And the total number of dots I put is the sum of the number of sides on the faces, right? But let's zoom out again. And every edge has 2 dots, one on this side and one on that side, because it separates 2 faces, okay? All right, and these things are true for connected graphs, which is a technicality, okay? I'm not going to get into it, okay? All right. So now, we are after something. These 2 things.
By connected, you mean that if you draw something somewhere else,
Yeah.
these 2 don't have anything to do with it.
Yeah, so for example, technically, if I draw this is a graph, okay? It's a graph which has 2 vertices, no edges, right? But here, v is equal to 2, all right? And you only have the outer face, okay? And, you know, edges are 0. So it'll be violated. You'll get a 3 there, right? Yeah, so, okay, yeah, but in this case, yeah, I mean, what it says is these really are 2 graphs which have nothing to do with each other. One can think about this. So there's a technicality, little technicality there. Okay, so now we have, okay, so 2 times the number of edges is equal to the sum of the sides of the faces. Okay, now one thing is that every face must have at least 3 sides. Okay, it's not, you know, possible to make a face with just 2 sides, right? So the smallest face that you can have is 3. Okay, so this quantity, some of the sides of the faces, I have a lower bound on it, right? And what's the lower bound? This should be at least 3 times the number of faces. Okay, because each face is going to give me at least a 3. Okay, it may give me 4, it may give me 5, it may give me 7. So I will get at least 3 times the number of faces. So what does this say? That 2 times the number of edges must be greater than or equal to 3 times the number of faces. Okay, so I have an inequality and I have an equality. So I should be able to manipulate this to get rid of one of the variables. I won't get an equality, I'll get an inequality, but you know, I should be able to do this. And what you do is you want to get rid of the faces. Okay, so let's do that. And how do I do that? So let's multiply this equation with 1/3, right? So we'll get 2/3 here, and I'll get rid of this f. Okay, and so I can put a minus here and write that. Okay, so that so far I've not done anything illegal. And then I can take my second equation. Okay, and now I can add these 2 and I'll get an inequality, right? My inequality would stand. So I'm adding this side to here and that side to here. So what do I get here? A V minus a third E is greater than or equal to 2. I added, right? Okay. So I just manipulate this a little bit. I multiply this by 3, so I get 3V minus E is greater than or equal to 6. And now I write E there and bring the 6 there. So E is less than or equal to 3V minus 6. Okay, this is what I was after. Okay, so what does this equation tell me? This equation tells me that the number of edges in a planar graph is linear in the number of vertices. In fact, less than 3 times the number of vertices. Notice that if you have n vertices, the total possible number of edges in there is quadratic. It's actually, you can do it, n choose 2, which is n times n minus 1 over 2. So a graph can have, a quadratic number of edges. So planar graphs are very sparse. This is what it's saying. Okay. All right. So why did I do all of this? Is because I needed to prove this lemma. Okay. All right. And the lemma says that every planar graph has a vertex with, not with, let's write of degree at most 5. Okay? All right? And how do I prove this? I'm going to use this result, right? Edges is less than 3V minus 6. Let's multiply it by 2. So we get 2 times the edges is less than 6V minus 12. Okay? But remember, twice the number of edges is the sum of the degrees by the handshaking lemma. Okay? So this is saying that the sum of the degrees is less than or equal to 3V minus 12. Okay? All right? Now what happens if I divide this by V? If I sum up the degrees and divide them by V, I get the average degree. Okay? Every vertex has a degree. I add them up, divided by the number of vertices. So I get the average degree. And if I divide this by V, I get a quantity here which is strictly less than 6. Right? Okay? So this tells me that the average degree is strictly less than 6. All right? So the minimum degree has to be strictly less than 6, but degree is an integer. Okay, so it can't be, 5.3. It must be, there must be a vertex of degree strictly less than 6. And sorry, the only other possibilities are 5, 4, 3, 2, 1, and all that. Okay? All right. Okay. And now, if anyone will prove the 6-color theorem for me. Okay, not the 5-color theorem, but the 6-color theorem. Okay. Okay, so I have this planar graph and I have vertices here and I want to color them with 6 colors. Okay, I use my theorem and I say find me a vertex which is of degree less than 5. 1, 2, 3, 4, 5. Okay, let me delete this vertex. Now, let me throw this out. I get a smaller problem. Okay, now this smaller problem can be solved by induction. right? So I have a smaller problem, so I will solve it by induction. So I can assume that the smaller problem, the graph was colored with 6 colors. Okay? Now I have a solution for the entire graph except for one vertex. This vertex I don't know the color of. Okay? So somehow I have to choose a color for this vertex only. This is the beauty of induction. You know, you just have to show how to go to the next step, or you go back and you can assume that you have solved it already. Okay, so I have to choose a color for this vertex, and it is only connected to these 5 other vertices. Hey, but I have 6 colors. Okay, so one color, there must be a color that doesn't appear on these 5 vertices. So I have a 6th color available, which I'll give it. Okay. Charyar, are you comfortable? Okay. Or shall I repeat the argument?
So we have how many vertices?
No, okay, look, the total graph that you, okay, so if I become very pedantic, then I have to do induction. So I'll have to prove this for n equals 1, the base case. And I'll have to prove this for that I can go from the case for n vertices to n plus 1 vertices if I want to be very pedantic. Now, what is the statement I want to prove?
This is for induction, not for the case where you can do it for any n.
Yeah.
You just talked about 5, 6.
Okay, yeah, all right. So n is equal to 1 is our graph. I want to prove that every graph on n, every planar graph, okay, so put that, on n vertices is 6 colorable, right? Okay. Now, the base case is trivial. If I have only one vertex, I can give it any color I want. If I have 2 vertices, I can give, up to 6, it's actually trivial. I have enough colors available. So all I have to do is show you the induction step. All right? So assume that this statement is true for a particular n. All right? And then I have to show you that it's true for all graphs of size n plus 1. So give me a planar graph of size n plus 1. Okay? So this is a planar graph and it's huge. It's huge and it's complicated. Okay? I don't know much about it. But what do I know?
The previous graph is 6 color.
Yeah, that all graphs of size n are 6 colorable. But for this graph, I know something. That there's a vertex of degree less than or equal to 5. Okay? And I say, the graph that you've given me, it has a vertex of degree less than or equal to 5. Please show me that vertex. All right? So you show me this vertex, 1, 2, 3, 4, 5. Okay? There may be other vertices which have higher degree. Okay? All right? And now I say, well, remove this vertex of degree 5. Yank it out. And now what do I have? I have a graph on one less vertex. Agree? Now that graph on one less vertex is by induction 6 colorable. I use the induction hypothesis there. So I say, okay, remove this vertex, let's color the rest of the graph with 6 colors for me. Right? So now I have n vertices which are colored. So this is purple, okay? This is blue, okay? This is green, and so on, right? And there are no conflicting edges, right? So now I say, well, I have managed almost to solve all my problems except for one vertex. Okay? So let me put back this vertex. Okay? This vertex has only 5 edges coming out of it. Okay? And to color it, I have to only worry about its neighbors. And there are only 5 of them. But I have 6 colors available, right? Okay? Some of those colors are not allowed there. All right, but 6 is 1 bigger than 5, so I always have 1 color available. Let me put that, okay, and now, bingo, my entire graph is colored. Okay, right? So that's where I use the induction hypothesis, right? Okay, all right. If you're a computer scientist, what you can do is you can think about, you pick a vertex of degree 5, you throw it out, you get one smaller graph, and you again pick a vertex of degree 5, throw it out, you get one smaller graph and like that, till you get a trivial graph. And then you color that and you move backwards. All right? And every time you add the vertex, right, the only 5 edges going to the already previous. So there are only 5 restrictions, but you have 6 colors. So you're never going to get stuck. Okay? All right? Okay. So that's, and we need to understand this argument to go forward because for 5-color theorem, to prove 5-color theorem, this basic argument would be there, but we'll have to do something clever. Okay? All right. Why can't I use this to prove the 5-color theorem? Only one bad case. I get a vertex of degree 5, and when I apply induction, there are all the possible colors here, right? And I can't.
There is no guarantee that there is a node with at most 4 edges.
Yeah.
उसकी
गारंटी नहीं है. अगर वो होता तो 5-color theorem बहुत easy हो जाता, right? But we don't have that guarantee. We only have this. So 6-color theorem is very easy. Okay. So now. How are we going to prove the 5-color theorem? It's going to be, the structure of the proof is exactly the same. The base case 5-color theorem is trivial up to 5 vertices. And then we will find a vertex of low degree, which is 5. We'll yank it out. Okay, we get one smaller graph. By induction, the magic of induction, the smaller graph is 5-colorable. Okay, and then we will get stuck. Okay, and then we'll try to be clever about it. Okay, so shall we do that now? Okay?
Yes, sir.
Okay. All right. So now I'm trying to prove that every planar graph is 5-color. Okay, and the structure of the proof is exactly the same. We will apply induction. Cases n equals 1 up to 5 are trivial. Okay, so base case we don't really have to worry about. And once again, I am going to I'm going to take a graph with n vertices or n plus 1 vertices. I'll ask you to find me a vertex of degree at most 5. Okay? And I will, so this is a very complicated graph. Okay? And I will yank this vertex out. Okay, I'll pull this vertex out, and then I get a graph on one smaller size, so I'm allowed to use the induction hypothesis, right? So that will color all the vertices for me except for this one. And I just have to worry about this one little vertex. Okay, I could get lucky here. What if this has degree 4? Then I'm done by the previous argument. I have one extra color. What if one of these a color is repeated, let's say red comes here and red also comes here, then I'm also done because all 5 colors don't appear there. The only time I get stuck is if the degree is exactly 5 and all 5 colors appear here. Okay, all right. So now I'm going to go a little aside. I need to ask you something, few things. Okay. All right. So let me draw a graph here. Okay. All right. Do I want? Oh, let me. Oh, wait. Do this. Okay. Sorry. Let me think how I want to do this. Okay. Yeah, let me just do this very simple example. Okay. Here is this graph, right? And this is a planar graph. Okay. Let's say we color the vertices. Let's say I color this blue, and then I color this red, I color this red, and I color this purple, and color this purple. Okay? So this picture actually is showing me the planarity of the graph when I look at it. Okay? But there's another way for me to draw this, is what I can do is I can say, okay, this is, let's say, A, B, C, D, and E. I can say, let me put the colors, which are purple vertices, separately. Let me put the red vertices separately, and the blue vertex separately. Okay? Huh?
Why are we actually repeating the colors?
Oh,
Like why 2 purple, why 2 red? If we have 6 colors or 5 colors, then why we are repeating the colors?
oh, this here I've taken just a simple example. In this case, you don't need all 6 colors.
Okay.
You know, you can do it with few. So I'm trying to make another point actually, right? So for now, this is like an aside. So here, let me label them DB, and this is AC, and this is E. Okay, and you know, I can see the edges. From D, there's an edge to E. Okay, from D, there's an edge to C and A. From B, there's an edge to C and A. And there's an edge to E. And I think I have these edges, right? Okay, so these two are the same graph. They're different drawings of this. Now, this drawing is showing me the planarity of the graph. This drawing is showing me what is called the chromatic number, that this graph is 3-colorable. Now, what do you notice? What would be the...
This is not really a planar graph because the lines are crossing. The lines are crossing in there.
Okay, that's a very good point. This graph is actually a copy of this graph. They are the same.
If you could rotate it around in the plane, but you can't go outside the plane. If you could rotate it, then the crossing would go away.
Yeah. So the idea is this graph, let's call this G1, and this graph, they are the same graphs. They're different drawings in the plane. Okay? This happens to be a planar drawing. This is what we will call a non-planar drawing. Okay? So they are isomorphic graphs. You know, DC is connected here, DC is connected here. For example, AB is connected here. So if XY is connected here, if and only if it's connected here. So in that sense, they are the same graph. They're just two different drawings of it, right? So what the first drawing is showing us is the graph is planar, all right? And what the second drawing is showing us is that this graph can be colored with 3 colors, right? Here's color number 1, here's color number 2, here's color number 3. Okay, so you can draw different pictures of the same graph to sort of talk about different properties. Okay, this drawing is very natural when you want to think about it as a planar graph. This is a better drawing when you want to think about it as a graph which can be colored with 3 vertices. Okay, all right, so that's one observation. Now suppose if I have a graph which is colorable with 3 or 5 or whatever color, and I take all the vertices of one color, okay, and look at that set, what would you see? Okay, so a graph was colorable, let's say with whatever many colors, somebody had colored it, and you then go and look at what we call a color class, all the vertices with the same color. Let's say you look at all the red vertices. What kind of a set would you see? Would there be any edges there?
Between
Yeah.
those two?
Yeah.
These, no, because
No.
obviously because we want
Yeah.
neighboring regions to have different.
Yeah, we want neighboring vertices. If they colored it properly, I mean, when we mathematicians say coloring, we mean a proper coloring with the restriction that edges, the endpoints of edges got different colors. So then when I pick up all the red vertices, look at them like this, there will be no edges. Okay? And if I look at, all the blue vertices, so here were these blue vertices, the color blue, right? Okay? There will be no edges. But there will be edges between here. Okay? So when you're coloring the graph, what you're doing is something like you make a picture of it like this with different color classes, and there are no edges within those color classes. There are only edges going across. Okay? All right. So that's one observation. So when you're actually coloring the graph, that's what you're doing. Okay. Now here is another observation. Suppose you colored a graph with 5 colors. Okay? And I came and I said, wait a minute. I don't like your coloring. So I switch 2 colors. Would that be still a proper coloring? Sure. Yeah. If I permute the colors, it will be fine, right? If I switch the colors around, it will be fine. Okay, that's observation number 2. Here is observation number 3. Here is a coloring of a graph, and I'm looking, so there might be more colors here. Okay, so there are edges going, and the damn thing is a mess, right? So what I do is I only look at 2 colors, blue and red, let's say. Okay. Now, if I switch the colors of blue and red, that's fine, I get a proper coloring. But here, let me look at this closely. When I look at this blue and red and only that part of the graph, what do you notice? Only this part of the graph. No, that was unintended, if it is. It's disconnected, 2 pieces, right? It's like inside here there are 2 graphs. There are these vertices, okay, and then there are these vertices. That's what I intended. That's why I got this mixture paint. So if, let's say, I go to 2 color classes, all right, and I zoom in and I see 2 connected components, of course I can flip those 2 colors, but what if I just flip the colors of one connected component? Suppose I say, wait a minute, I'm going to turn these into red, okay, all right, and I'm going to turn these into blue, okay, all right, but not those. Those one will keep their colors. Would I get a proper coloring? Yes, right? Because, yeah, it doesn't make any difference. I can just flip only one component inside there. I don't have to flip both components because, these, obviously when I flip these guys are the only ones which could create a conflict, but there are no edges between those, right? So that's a very important, that I can flip just one component. Okay. Now we are ready to prove the 5-color theorem. Okay, all right. Okay. Okay, so remember our 6-color theorem plan that we always had in mind. Find a vertex of degree 5, yank it out, color the smaller graph by induction. Your problem is almost solved. You have just one vertex to worry about. Right? And if you can manage that one vertex, you're home. The beauty of induction, right? So here's your vertex, and it was connected to 5. Okay. And of course, I should draw a little bit of that this is a very ugly, complicated, extremely nasty graph, but it's planar. Okay, all right. So what do? Is I yank this vertex out, okay, and I call the magic of induction and say, color the smaller graph for me, please. Okay, and induction magically returns that coloring for me, and then I look at the neighbors, the 5 neighbors of this, and one of them has green. Okay, purple, okay, red, blue, okay, I have red, and white is a color, okay, so, and white, okay, and this is the only bad case when all 5 colors appear. If only 4 colors appear, I'm home free. Okay, so 5 colors appear. Okay, now I'm going to try to use that thing. So I go to red and color green. So these are all the vertices which are, and I look at the other picture, the chromatic picture. This picture is there, so these are red vertices. Okay, and let's say these are green vertices. Okay, and let's give these a name. This is A, which is green, and it has to be somewhere here. A, and this is B, which is red, which is somewhere here, let's say. Okay, right? And I go and look at these 2 colors, and I do this kind of thinking here. All right? I look at the connected components inside. Okay? And let's say that the connected component of A and B are different. Okay? Okay? If the connected components of A and B are different, then you agreed that I could switch the colors only in one connected component. Okay? So I switch them in this connected component. So B becomes green. Okay? This becomes green, which may be somewhere else, and these become red. When I go and look at the coloring in this picture, all of a sudden, this has become green. Okay, and now red is available for this.
And the main assumption here is that the 5 vertices attached to our central vertex, they are not connected to each other.
No, they may be. Then why not? That doesn't hurt me. This has only 5 neighbors. That is, I only have to worry about these 5. It's not connected to anybody else. So all I'm trying to do is get a repeat here. And this is a trick to get a repeat. Okay. So if these two happen to be in different connected components, I'm home. I'm done. Okay? Yeah?
So then we have to prove that there would be A and B that would be in different connected components.
Yeah.
Have you proven that?
No, I haven't. No, I haven't. So I am not done yet. Okay? So the thing is, what is the bad case? Well, the bad case is that A and B are in the same connected
That was
component.
my question.
In the same connected component. Now when I do the switch, A and B keep switching colors. Red goes here, green comes
Yes,
there.
exact.
And I haven't solved the problem. And so, that doesn't work. Okay?
Yes.
But before we rush to euthanasia clinics, we should give this one more try. Okay? All right. What does it mean for A and B to be in the same connected component? Okay?
They're connected.
There is a path which goes from A to B. Okay? In this graph, I can go from A, reach B. Okay? So this path it goes green, red, green, red, okay? Green, red. Luckily, I had the parity right, otherwise I would have had to put one more. So there's a path that goes from green to red. Yeah.
So if we can't find the two colors or the pair of points that are in different connected, then we have to include the third color also, right?
Okay, yeah, I'm coming to that, right? So there is a path which is going from here to there, okay? And if you include this vertex, let's call it V in it, it's a cycle, right? These two vertices are inside, and this one is outside. So I can play the same game now with white and purple, okay? I can play the same game now in white and purple, and before I destroy something useful, I come here.
So there must be a crossing somewhere. That's what we are trying to get to, right?
Yeah.
So we can't have this without it being a planar.
Absolutely.
So
Okay,
violate
so-
planarity.
Yeah, so here I have white vertices, okay? All right, and then I have purple vertices, okay? And I identify these two vertices, let's call them X and Y. Such creative names. Okay, there's X and there's Y somewhere here. Okay? All right, now if X and Y happen to be in different connected components, then our job is done. Otherwise, there is a path from Y which reaches X. Okay? But then that path must cross. And that's not possible. Okay? And that ends the proof. Okay, so either blue and green will work. If that works, you're home free. Or white and purple will work, and you're home free. Okay? Right? Okay, think about what if you claim that there's a path, it has to go to a purple vertex, all right? It remains outside, it has to somehow enter the cycle. And that it cannot do without crossing. That's the Jordan curve theorem, right?
Inside and outside.
Yeah.
So can't we use the same argument for the four color theorem? Why
No.
is that not possible?
Yeah, so that's your homework, to convince yourself that it doesn't work for the four color theorem, okay? All right? Okay? So, really beautiful, huh?
Great.
It's really a lovely proof.
Awesome.
Yeah, okay, so now let me tell you, so the 1971 Oppel and Hawken proof was the first major proof that used computers. Okay, so their theorem is something like this. They say the four-color theorem will be true if and only if it is true for the graphs generated by this algorithm. Okay, and that algorithm generated only a finite number of graphs. Okay, and then those graphs were actually colored using a computer search. Okay, so it was at that time it had started a big debate whether computers could be used to give a mathematical proof. And there were heated arguments. So, for example, you have not proved that the compiler that you have used is correct. You don't have a proof that your Fortran compiler doesn't make a mistake, right? So is this really a mathematical proof? Those kind of questions came up, okay? But now it's become routine to use computers in this thing. Okay, how much time is there? Okay, 7:15?
7:15.
7:15. Okay, so in the abstract I promised something, so let me go ahead and do that. One should fulfill their promises, right? So, so this was reasonably clear to everybody?
Yes.
Okay, good. All right. Okay. So now here's a notion of what is called choosability. Okay. So in the coloring case, what you have is you have a graph, and you're trying to color vertices such that no edge is monochromatic. That's a mathematical way of saying it. That every edge has at least two colors appearing on it. Okay. Now in choosability, what you can do is you have a graph, and it doesn't have to be a planar graph. Okay, with vertices and edges. And so you have vertices V1, V2, V3, all the way up to Vn, right? And let's say you want to prove that a graph is 5 choosable. Of course, you can talk about k choosability also, but 5 choosable. Then what you're going to do is you imagine as if each one of these vertices is a little person, right? And this person will tell you what colors are acceptable to them. Okay, so you have this set of colors which could potentially be infinite, doesn't need to be infinite, just 5 times n will work. Okay, so this person said, look, I like red, okay, and I like green, and I like blue, and I like orange, and I like, white. Okay, right? And the second person says, well, these are the colors that I like. And they may actually give the same colors, or they can give different colors. For example, they can say, I like brown, I like, lavender, okay, okay, so they give you these choices of the color. So it's like you go to Punjab and, you ask the people of the district which colors are acceptable to you, all right? And of course, if they give you only one color, then there will be conflicts, right? If two adjacent districts both said blue, blue, then you will be able to, if you try to satisfy their requirement, you won't satisfy the requirement that edges are, not monochromatic. So you have to tell them, look, you can't just have one alternative, give us more, all right? And if for every possible choices that people can make, you can satisfy their requirements and color the graph so that the edges have different colors, then that graph is called 5 choosable. Okay, so it's a far more restrictive thing. If all of them choose the same colors, then it reduces to chromatic number. If all of them just choose the same color.
V1 and V2 can have common colors or not?
Yeah, common colors too. Yeah. Yeah, yeah. Okay. Now, when I first heard about choosability, I was like, wait a minute. If two people are choosing exactly the same colors, then it's like the chromatic numbers. If they are choosing some different colors, then shouldn't it be easier to satisfy their requirements? Because, you know, if these two guys only have two colors in common, you know, their three choices are like automatically going to, right? So it seems like the problem should get easier, but it doesn't. Okay, there's a lovely theorem which says that there are graphs whose chromatic number is 2. Okay, you can color them with two colors, but their choice number is arbitrarily large. So their choice number is 3 trillion. Okay,
Choice number, what's the choice?
is the minimum number of choices
Minimum.
people so that they can be satisfied. So if you want to force a coloring on those people, 2 are enough. If you want to give choices to people, you'll have to give them 3 trillion choices each. Okay, so it's a very interesting.
If there are two vertices that are not connected,
Yeah.
then they can have an identical set of choices.
No. Yes, they can. There is no restriction on the choices. Yeah, yeah. So if two vertices are not connected, then the thing is you can give them the same color. Okay? It's like in a planar graph, these are countries that don't share a border. Right? So then you can give them the same. Okay. So let me. Okay, so this is a little tricky, and I'm going to try. And so you people are, in some sense, I'm experimenting on you. Okay, all right. So here is the conjecture, or now a theorem. Every planar graph is 5 choosable. Okay, and I like this theorem better than the 5-color theorem. A, because it's a bigger theorem, in the sense more general. 5-color theorem is a sub-theorem of this, so it's a special case of this. The second is this 5 can't be improved. Okay, so the 5-color theorem that we proved is not really the best possible. You know, 4 is the best possible, but in this case, the choice number is known to be 5. Okay, so we can do that. Okay, and the proof is surprisingly easy, you know. Surprisingly easy, but it's very tricky. The thing is that, okay, so I want to explain something. So sometimes what happens in mathematics is harder things are easier to prove. Okay, it's not obvious, but that, you know, it's counterintuitive that harder things are sometimes easier to prove. So I can explain to you one of the reasons is, let's say you have a statement P and a sequence of statement P1, P2 that you want to prove by induction. Okay, and you have a sequence of stronger statements. Okay, Q1, Q2, and Qn. Okay, so somehow P's are contained in this. So these are stronger statements. When you apply induction to the weak statement, remember that your induction hypothesis is also weak. Okay, so you have less to work with. Of course, less to prove. Okay, less to work with, but less to prove. Here you have induction hypothesis is a stronger statement, so you have more to work with, but more to prove. So it's not obvious that the first one is easier than the second. Okay, you know, it really. So in this case, the person actually who did this, he found the right strengthening of this statement on which he could apply induction. Okay, and finding that was I think the brilliance. Okay, so here is his statement. His statement is that take a planar graph. Okay, I'm not going to make this very complicated. Okay. Okay. Yeah. And let's see, do this. All right. And give me not 5 choices. Okay. So this is called the outer cycle, right? And he takes a graph which is what we call triangulated, which means all the regions inside a triangle. You know, if they're not, for example, in this one it's not, just keep adding edges. You're making the problem only harder by that, right? Okay, so he says, don't give me 5 choices on the outer region, give me only 3. Okay? Choices for the outer face. Okay? All right? So instead of 5, just give me 3 choices on the outer face. Make my life even more difficult. And you get to pick the color of one edge on the outer cycle. So, you know, you can tell him that this vertex should be blue and this vertex should be yellow, right? Okay? And there will be vertices which will be in the interior. Okay? All right? Like this, it will be a planar graph. For each interior vertex, give me 5 choices. Okay? So interior regions get 5 choices, boundary regions get 3 choices, plus you mess up his game by choosing the colors of one edge on the boundary. He says, even if you do this, okay, I can turn this into a proper coloring. Okay, I will color the outer vertices such that their colors come from their 3 choices. I will color all the inner vertices such that their color comes from their 5 choices they have given, and every edge will have different colors at the end point. Okay, so it's a very contrived kind of a statement that he does induction on.
Which 2 colors he will choose?
Oh, the adversary chooses that.
How will you predict? How will you predict the colors the adversary will choose?
They will have to choose 2 different colors from
Yeah.
the lists that are given.
Yeah.
And they can choose any of them. So he's claiming you can do anything you want.
Okay.
Yeah, he can't predict, you know. That's the beauty.
I'm talking about you. Like you are saying that even if he is choosing the 2 colors, the rest is in your hand. Again, there will be different colors used in the graph.
Yeah, so for example, let's say he chose blue here, right? I will not change these colors. I have to choose a color for this, this, and this, right? So for this vertex, how many choices do I have?
Remaining 4.
No, I have 3. Remember,
3.
remember
Okay,
3
okay,
choices
okay,
I
3.
have. Blue is out.
Yeah, 3.
Okay, so obviously if there is blue, I'll throw that out and I'll work with the other colors.
Okay, who will be choosing the colors first, you or the adversary?
Okay, the colors are, yeah, the adversary.
The adversary.
Yeah, the adversary. Yeah, the adversary. You know, they give me the list of colors.
Then it is easy.
Okay, all right, okay. And how does he prove this? So let me so this statement he's going to prove by induction. All right, now for n equals 3, this statement is obvious. There are only 3 vertices, they are all outer vertices. If you've given me 3 choices everywhere, I put 1 color here, remove that from here, put 1 color here, remove the 2, and put 1 color, I'm done. Okay, so the base case is obvious, is easy. Okay, now this is what the proof says. The proof says, well, look at this edge, this green edge that I've drawn here. It is actually connecting 2 boundary points, right? 2 boundary points. So it's sort of cutting the graph in 2 pieces, all right? So suppose you find an edge that connects 2 boundary points, okay? Then you see a smaller problem here,
Yes.
okay? All right? So you see a smaller problem here, and so you solve this by induction, the magic of induction, right? Because we assume the case, and it's exactly a smaller problem. On the outer, you have 3 choices, okay? On the inside, you have 5 choices, and one edge on the boundary is already colored. So it exactly fits the hypothesis. And so this is 5 choosable, right? So this is 5 choosable.
Makes it easy.
Okay? When you do that coloring, that will put some color here, here, okay? And all that, okay? Once you have solved this problem, look at this problem.
Close again the boundary.
Is that a smaller problem?
Yeah.
Exactly. Now this edge is colored, right? 3 choices for all the boundaries and 5 for all the interior vertex. Right? So you're done. Okay? Okay? Is that too... anyone convinced with that argument?
3 choices किस तरह होते हैं बाउंड्री के मतलब assumption है
हाँ वो तो पहले से ही दिया हुआ था ना हाँ तो पहले मैंने ये वाला प्रॉब्लम छोटा वाला सॉल्व किया ठीक है ना अब मुझे बाकी इन वर्टिसेस को कलर करना है ना तो दूसरा मैंने ये छोटा वाला प्रॉब्लम सॉल्व किया
So instead of solving the whole graph,
I
at
solved
the same time you broke the graph in smaller graphs and
yeah so I solved this side of the problem by induction and then I solved this side of the problem.
Suppose you had many vertices down at the bottom part.
Yeah.
Suppose
Okay.
you had many vertices down there.
Yeah. So
On the boundary.
Huh?
On the boundary, many more vertices.
Huh.
Then you would divide into some more parts.
you know I'm not saying that the problem gets halved. Okay? So I'm just saying problem is broken into 2 smaller parts. All right? So if I have in the graph if I had n vertices, this side will have strictly less than n vertices and this side will have strictly less than n vertices. So there is this what is it called? It's sometimes called the strong form of induction, right? That you assume that you can do the thing for all smaller numbers, not just for -1.
I remember you used to teach us to solve the problems by breaking into smaller functions.
Well, yeah, that's a different thing. That's programming, yeah. Okay? So is this, Shahryar, are you okay with this?
तो आ गई लेकिन मतलब बहुत अजीब लग रहा है मुझे बहुत ही वियर्ड किस्म की मूव लग रही है मुझे ये कि मतलब वी अज्यूम दैट आउटर एजेस वर 3 चूजेबल ऑल इनर vertices were 5 choosable.
हर आउटर एज पे 3 वर्टिसेस थी, लेट्स से रेड, ग्रीन, ब्लू. ओके, इस पे चॉइसेस थी ऑरेंज, पिंक, ब्लू. ओके, इस पे चॉइस थी ब्लैक, व्हाटएवर. ठीक है, 3 चॉइसेस थी. इनर पे 5 थी. ठीक है ना. तो अब हमने जिसका ये वाला जो सब प्रॉब्लम देखा है, तो इसकी आउटर बाउंड्री तो ये है ना. इसकी क्या आउटर बाउंड्री पे हर पे 3 चॉइसेस हैं? हाँ है. ओके, इसके इंटीरियर में 5 चॉइसेस हैं? हाँ है. और क्या इसकी एक एज ऑलरेडी कलर्ड है? हाँ है. सो इट फिट्स द क्राइटेरिया, राइट? सो बाय इंडक्शन दिस पार्ट वुड बी 5 choosable. So let me color this in that way by induction. Now this new edge has been created. Okay?
But that was only an assumption. How do I know that the smaller part could be 3 choosable and 5 choosable? What if it was a very large graph?
By induction. Okay. This, is this statement trivial for n equals 3?
Yes.
Yes.
For that we can understand that it
Okay.
can be done, but
So-
for very large
Okay,
graph.
so but for base case is done, right? Now I want to do the inductive step. Okay, so for that I assume that this statement is true for graphs of size 3, 4, 5 up to n. Okay, it's true for all smaller graphs. This is called the strong form of induction. Okay, all right. And now I say, well, you know, you've given me this bigger problem. I find this diagonal, right? And I concentrate on this part, and it's a smaller problem. Okay, and all the hypothesis is satisfied, so I can conclude that I can color
No,
these.
but in induction we prove that the statement is true for the base case, right? So we have proved it for base case n is equal to 3, but we haven't proved it for 4, 5, 6, 7 up to n. Don't we have to prove that first as well?
Oh, okay, all right.
Because in strong induction we are assuming all of the cases.
Yeah. Okay, so I have to explain a strong induction here. So let me explain. Okay, strong induction. All right. So induction is this. Okay, that if P of 0 or 1, कहीं से भी आप start करते हैं, P of 1 is true, number 1, you establish that, and then you establish that P of n implies P of n plus 1. Okay, you prove this for all n. You are n greater than or equal to 1 actually. You know, हम classical कर रहे हैं. तो यहाँ से आप conclude करते हैं कि for all n, P of n is true. Right? This is classical induction. Right? Do the base case, assume the induction hypothesis, and then do the inductive step. Right? Do it the next. So this is called induction. Now what is the strong form of induction? Okay? What's the strong form? It says that if P1 is true, so do the base case, right? And if P1 up to Pn imply Pn plus 1, okay? Then for all n, P of n is true. Okay? So this is the strong form. ये कह रहा है कि आप सिर्फ पिछला वाला इंडक्टिव हाइपोथेसिस ना लें, आप सारे अस्यूम कर सकते हैं 1 से लेकर उधर तक. Okay? Now, here's the thing. Let me give you a proof that every integer can be factored into prime numbers. True for other than 1, sorry. Wrong statement. 2 के लिए true है, 2 is a prime. 3 के लिए true है, 3 is a prime. The base case is
2 and 3.
ठीक है ना, जो भी आ गया. अब inductive step क्या होगा? I take a number n, it's either a prime, then I'm done, or it is composite. Okay? So if n is composite, then it's a product of two numbers smaller than it, a and b. Okay? Now by strong form of induction, a can be factored into primes. And by strong form of induction, b can be factored into primes. And then I put those together and I have factored n into prime. So this is, here I'm not using the weak form or the standard form of induction.
ठीक है, मुझे समझ तो आ गया, लेकिन बड़ा मैजिकल सा लग रहा
नहीं
है.
है
और जो
magical,
स्टेटमेंट है ना, वो व्हाई डज ही नीड टू हैव द इनसाइड वर्टिसेस बी 5 चूजेबल. उसका क्या रीजन, उसका क्या
I
तो क्या
haven't finished the proof, that's why. You'll see that. नहीं मैंने अभी प्रूफ फिनिश नहीं
उसकी
किया.
तो जरूरत ही नहीं पड़ रही.
हाँ नहीं उसकी ज़रूरत पड़ेगी, that's why I'm going to. So लेकिन ये थोड़ा बेसिक है, ये मैं ज़रा समझा दूँ.
ठीक है, समझ.
Okay. Strong form of induction जो है, okay, all right. how can I convert strong form of induction to regular induction? Okay, all right? And it's just one line trick. This is a strong form of induction, okay? Instead of this, I will write a statement which will be like a weak form or standard form of induction. So let's define Q of 1 as P of 1, okay? Q of 2 as
P1 and P2.
okay, Q of 3 as P1 and P2 and P3, okay, and so on. Okay, Qn is equal to the its conjunction of the first n p's. Okay, regular induction on q's is the same as strong induction on p's. So strong form of induction is not really strong.
We can also write Q3 is equal to P3 and Q2. Like we have already
Yeah,
said
you can be efficient with it, yeah, if you want. Yeah, you can be efficient with it if you want. But this is much clearer to me. Okay? So, look, induction is about breaking the problem up into two smaller, similar problems. Okay? As long as those smaller problems are strictly smaller than the one that you are at, you're home.
if not break them again, if not break them again, if not break them again.
No. Then you're not doing that. Then you're actually spelling out induction. Okay?
We are not supposed to do that.
Well, I mean, if you want, you can. But induction says if you have just broken up the small problem into two similar smaller problems, you're done. Your proof is over.
Okay, thank you.
Okay? ठीक है? Okay. Acha, अब with strong induction behind, okay, now let's get back to this proof and we'll do that. So ये हमारे पास एक ग्राफ है, उसकी एक एज को किसी ने कलर किया हुआ है, right? और हर आउटर वर्टेक्स पे 3 चॉइसेस हैं, हर इनर वर्टेक्स पे 5 चॉइसेस हैं. अब अगर दो बाउंड्री वर्टिसेस आपस में कनेक्टेड हैं तो ये नेचुरली ये प्रॉब्लम एक छोटा बन जाता है. ठीक है, ये बाय स्ट्रॉन्ग फॉर्म ऑफ इंडक्शन सॉल्व हो गया. अच्छा, जब ये सॉल्व हो गया तो इस एज पे कलर आ गए ना, तो यहां पे आ गए ब्लू और यहां पे आ गया येलो. ठीक है ना, और मेरा प्रॉब्लम क्या बचा है अब? सिर्फ ये. Okay, and magically that is also a similar problem, exactly similar problem. One edge is colored, you know, there are 3 choices here, 5 choices on the interior. So when does this argument doesn't work?
When you can't find a
When you cannot find a diagonal.
diagonal पूरा नहीं मिलेगा.
Yeah, when you cannot find a diagonal. So here, okay, so the bad situation is not that. That was actually the easy part. Okay?
Easiest.
Yeah. Easiest part. The bad situation is actually here. Somebody has colored this edge. Okay? All right? Okay? How many choices they have given you on the outside? 3. How many choices on the inside?
5.
5. And now you can't find a diagonal, so this oh God. Okay, to make the illustration better, let me let me choose the edge. क्योंकि यहाँ पे वो इतना अच्छी illustration नहीं बनेगी. So let me choose the edge here. Let's say somebody has colored this already red and this already blue. ओके और आउटर पे हमारे पास 3 चॉइसेस हैं, इनर पे हमारे पास 2 चॉइसेस हैं. सी नाउ आई सीम टू बी stuck and I have made this a very bad illustration. Okay. All right. Okay. Okay. Now what I do is I look at this vertex, right? Okay. This vertex, how many colors do I have here? 3. Okay. अच्छा, ये vertex तो हो गई है red, right? तो हो सकता है इसमें red हो, वो तो मेरा ज़ाया हो चुका है because I can't color it red. Okay. So बाकी 2 बच जाएंगे मेरे पास. अगर मेरे पास 3 बचे तो मैं कोई भी arbitrarily फेंक दूंगा, मेरे पास सिर्फ 2 बचेंगे. So I will work with only these 2 colors here. Let's say the choices here I have are green and yellow. ठीक है ना? अच्छा, अब इसके नेबर्स को देखें. इसकी एक तो ये आउटर है, बाकी इसके इंटीरियर्स के ये नेबर्स हैं. ठीक है ना? राइट? इंटीरियर पे कितने चॉइसेस हैं? 5. उनमें से मैं ग्रीन और येलो उड़ा दूंगा. ठीक है? तो इसके इंटीरियर नेबर्स में मेरे पास कितने चॉइसेस बचे? 3 चॉइसेस बचे. और अब मैं इस वर्टेक्स को डिलीट करूंगा तो ये जो इसके नेबर्स हैं, राइट, ये जो इसके नेबर्स हैं, दे गो एंड बिकम द वर्टिसेस ऑन द आउटर साइकिल. Right? Okay. They become vertices on the outer cycle, but I have 3 choices on them now. Okay? And I have a graph on one lesser vertex because I've deleted this vertex. So then I say, magic induction, do the problem for me. That induction does the problem for me. And wonderfully, in अंदर वाली vertices में green और blue, green और yellow नहीं आ सकते. लेकिन यहां ग्रीन या येलो आ सकता है, लेकिन ब्यूटी इज कि 2 नहीं आ सकते, दोनों नहीं आ सकते. दिस इज जस्ट वन वर्टेक्स. तो अगर यहां ग्रीन आ गया तो आई हैव येलो फ्री हियर, अगर यहां येलो आ गया तो आई हैव ग्रीन फ्री हियर. दैट्स व्हाई यू वर नीडिंग दिस 5 कलर्स इन द इनसाइड. या
5 आर्बिट्ररी सा लग रहा था.
हाँ,
बाहर की 3 की तो समझ आ रही थी, लेकिन अंदर की फिर क्यों 5 चाहिए? अच्छा, सही.
Okay, so let me just see if I can. वो बहुत cluttered figure थी. I think here it will probably, if I can make red and blue. Okay. और हम किसी भी साइड पे काम कर सकते हैं. And this had, and then these were all triangles. You know, I should have made sure वो पिक्चर में अच्छी बनवा था, right? और ये है, okay? और हम क्या करेंगे कि ये वाली वर्टेक्स काट देंगे, right? ये वाली वर्टेक्स काट देंगे तो ये 1 2 3 4 वर्टिसेस आउटर साइकिल पे आ जाएंगी. ऑलराइट? लेकिन यहाँ पे हमारे पास 5 चॉइसेस थी. इस बेचारे की एक तो इसने खा ली, तो बाकी इसके पास ग्रीन और क्या बचा था? येलो. राइट? तो इसके पास ग्रीन और येलो बचा था. वुप्स. ओके. तो हम इनके लिस्टों में से ग्रीन और येलो उठा के फेंक देंगे. तो इनकी लिस्टें will go down by 2, but that's okay because now these are outer vertices. So in the next graph you have 3 on the choices on the outer vertices. Inside vertices में 5 की 5 हैं. Okay, and then the trick is, since I took out yellow and blue from here, I don't have to worry about these anymore. They'll automatically get no yellow, no blue. But I have to worry about this vertex. But this vertex can't be two colored. It can have only one color. I have two available choices. Okay. This proof is actually in this book called Proofs from the Book. Okay, and it is very tricky. It's very clever. Very clever.
And we can also prove that 5 is the minimum choosing number, right?
Yeah, you can make
Using the
graphs.
same.
Yeah, you can make graphs in which there are which are not 4 choosable. You can make such graphs. Okay. In fact, you can make graphs which are 3 colorable, planar graphs which are 3 colorable, but not 4 choosable. Okay. And the smallest such example is not very easy. उसको आप मतलब it's a paper. Guess by whom? Mirza Khani. Maryam Mirza Khani. And I have not only read that paper, but I have spent few weeks on trying to come up with a smaller graph. And obviously I had no chance because, Maryam is really, she's very smart. Okay? But I thought maybe my computer skills could help. So, I tried some ideas and did a lot of programming, let my computer run for 2-3 days. I wasn't able to do anything. So, I was trying to do a search of similar things, just playing with them. She's just too good. When she does something, it's very hard to improve on it. It's probably one of her very small works. Yeah. The smallest such graph is by her. So let's stop here, I think. आज का lecture कुछ लंबा हो गया?
नहीं, इतना ही हो जाता है मेरे ख्याल से। Thank you, sir.
Okay, thank you.